This lesson is on groundwater and water quality. Groundwater refers to any water stored below Earth's surface. When water soaks through the ground, it becomes groundwater, and we call this process infiltration. So just to reiterate something from our last lesson, infiltration refers to where water first soaks into the ground and becomes groundwater. Any movement of that groundwater underground after the fact is known as percolation. And I like to reiterate this because students often get infiltration and percolation mixed up. But again, infiltration is when water first soaks into the ground and becomes groundwater, and then percolation is any movement of the groundwater underground after the fact. All right, porosity refers to the amount of space between soil particles in the ground. High porosity means that there's lots of space between the soil, like you see in the bottom picture here. The grains are not tightly packed together, so you have a lot of space where water could be. Low porosity refers to a situation in which there is little space between the soil particles and there's not a lot of room for water to exist. And we also have scenarios where there is no porosity in soil, especially with clays that for one reason or another become tightly packed. There can be almost no porosity at all, and you really do not have much ability for that soil to take on water or allow water to move through it. Permeability is much like porosity. If you have high porosity, you'll also have high permeability, or if you have low porosity, you'll also have low permeability. And what we mean by permeability is a material's ability to allow fluids to pass through it. Okay, so with high porosity, we have high permeability, meaning water can travel through the soil easily. With low permeability, with low porosity, we have low permeability, and water cannot travel through the soil easily. If the ground is saturated, meaning it's already full with water, more water cannot infiltrate. We talked about this one with our geohazards lesson, and we explained that this is one of the main causes of flooding. You have ground that is already saturated or totally full with water. It's holding all the water it can hold already. So if you have precipitation after that, or if water flows in that area from somewhere else, it cannot soak into the ground and flooding occurs. So this is one of the main reasons for flooding. All right, let's talk about some areas underground in regards to the existence of groundwater. The first area we're going to talk about is the zone of saturation. That's this area down here where groundwater fills up all the pores in the soil. And you can see that's what we have here. This water has soaked through the surface of the soil and down through until it settles here in the zone of saturation, where water is filling all the pores. Above the zone of saturation, we have the zone of aeration. Now, this is a porous and permeable area. I mean, we kind of already know that because water has traveled down through it into the zone of saturation, but we're calling this area the zone of aeration because what exists in those pores at the moment is air. Now, if precipitation continued, the water table here, this boundary between the zone of saturation and the zone of aeration could rise because more and more water is filling up the soil. So the zone of saturation could get higher, or it could become larger while the zone of aeration becomes smaller, or we could go a long time without precipitation and potentially see a drop in the water table, and that would result in less water in the zone of saturation and a larger area or zone of aeration. And you can see this here on this slide on wells. So wells are a man-made apparatus. We drill a hole into the zone of saturation of an aquifer so that the groundwater can be extracted for our purposes. And extracting water from an aquifer is one of the things that can cause the water table to drop. And you can see that here. Water is being taken out of this well, and the water table's dropping, specifically right here around the well, and that's what we're calling this cone of depression here. All right, furthermore, aquifers can be depleted or completely drained if too much water is extracted in too short a period of time. Generally, as long as they're not damaged, aquifers can be recharged, meaning water can flow back into them. Either precipitation soaks down through the soil and recharges aquifer, or groundwater percolates in from elsewhere. But if you extract water more quickly than the water can be recharged in an aquifer, it can be completely depleted. And we've talked before about how if that happens, the soil can settle in on itself and pretty much lose permeability and lose porosity and not be able to hold water anymore. So this is a real concern, especially with wells dug to irrigate crops where lots and lots of water is being used very often. All right, ground subsidence or sinking can occur if water is used faster than it's replenished. That's more or less what I was just talking about. If we go back and look at this picture again, you can imagine if water is taken out here, some water pressure's some of what's holding the surface up. So if too much water is taken out and this soil starts to collapse in on itself, this ground level here can actually fall and become lower over time. Just like our example, the San Joaquin Valley in California that we've been talking about since day one in this class. Karst topography is landscape formed from dissolving of soluble rocks. That's kind of what you see here. You have underground rocks that are dissolving due to hydrolysis, and it leaves these depressions on the surface. And some of them can eventually open up to be sinkholes, because you can end up with spaces and voids underground, and when they're unable to hold the surface up anymore, that's when you have a sinkhole. A little more on groundwater depletion. Like I was saying, the San Joaquin Valley in California is an example. Excessive groundwater withdrawal over many years led to the surface level sinking by 8 meters over the course of roughly about 50 years. So you see in the picture, this was ground level in 1925, and then by 1955 it had sank to this level, and then by 1977, when this picture was taken, it was down here where the man is standing. All right, moving on now to water quality. All right, let's talk about types of water pollution. The first one we'll talk about is point source pollution. This is pollution of which the contaminants have a single identifiable source. You can see the source and say that's where the pollution is coming from. It's readily identifiable. We're talking about smokestacks, drain pipes, large-scale dumping. I mean, imagine something like a factory that is releasing wastewater into the environment. It's some kind of source where you can tell. Sometimes this thing, we have farms listed on point source pollution and non-point source pollution, but sometimes farms can count as a source of point source pollution if it's readily identifiable that the pollution is coming from the farm. Now, a non-point source pollution is not easily identifiable. This is pollution for which the contaminant sources are small scale, there's many of them, and they're widely spread out. So in this case, a lot of times pollution can kind of almost go unnoticed because it's coming from many, many small sources, and it's not really easy to identify the source and correct it. So we're talking about fluids that leak from cars. We're talking about pesticides, fertilizers, animal waste that comes from farms, household waste, pollution from things we throw away at our homes, or chemicals we wash down our drains, pet droppings when they break down and are carried into the soil by water, or carried into other water sources when by runoff from precipitation. All these kind of things can count as non-point source pollution. Major sources of point source water pollution. Agriculture is considered to be the biggest water polluter due to the use of fertilizers and pesticides, and also with raising livestock. Like I said, you have animal droppings, and they break down and they're carried by water into other sources of water or into the soil. And then industry is also considered to be a major source of point source water pollution. You have factories and power plants that produce waste. Now, this slide says that agriculture is the biggest water polluter, but I like to be a little more specific and think about it in terms of kind of right where you are. In rural areas, agriculture is definitely going to be the biggest water polluter, but in urban areas, that's where industry is going to be a bigger polluter than agriculture is. Mining is also a big point source polluter. We've talked about that in our lesson on human impact on the lithosphere. Mining releases toxins, acids, and sediment into the environment. These can end up in waterways as well. All right, a little more on non-point source water pollution. Non-point pollution reaches bodies of water through runoff. That's when precipitation falls on the land and cannot immediately soak into the soil for whatever reason, and it goes to water sources. Streets, sewers, infiltration, and percolation. Those are all ways in which non-point pollution reaches bodies of water. Pesticides, fertilizers, animal droppings from our pets are washed off of our lawns and end up in waterways. Cars leak fluids, like I was saying earlier. And it's estimated that 96% of water pollution is from non-point sources. A lot of times when we think about water pollution, we think about those point source pollution sources because, like I said, they're more readily identifiable. And we know in the past measures have been taken to prevent factories and farms from polluting the water. And but we can't readily see these non-point source pollution sources, and sometimes we don't even realize we're contributing to them when we do, and it's a lot harder to manage and a lot harder to control for, and controlling and preventing non-point source water pollution is largely up to us regular people. We have to be mindful about what we're doing that could potentially be a source of water pollution. And I'd like to say, you've probably heard me in class complain about the fact that so much garbage ends up on the side of our roads, even out here in the rural areas where you think there wouldn't be as much littering or pollution. You've heard me, one of the reasons I complain about that is because that stuff breaks down, and that plastic, when it breaks down, it ends up in the water, even if if it breaks down small, if you can't see it anymore. I mean, it's still there. And that causes, animals and us humans a lot of problems. A lot of us we don't even realize how much plastic we actually consume through water, because it's just hard to know that it's there, and also it's coming from so many different sources, like I say, and none of which are readily identifiable. All right, wastewater treatment plants. So water goes to treatment plants after it's drained or flushed, especially in cities where they have sewers. That water will go to the treatment plant to be cleaned up and put back into the water supply. Not all harmful substances can be detected and removed, and they're honest about that at the wastewater treatment plants. They'll tell you right away that they believe they're cleaning up the water really well, but they understand that there are some substances they cannot detect, and therefore they do not know whether they're removing them from the water or not. And like I said, this could include very small sized pieces of plastic that are just too small to detect. Industrial wastewater, sewage, and storm runoff contain toxic substances that aren't always removed. So it's not always just plastic. It's other chemicals and materials as well. So this is just important to know. I mean, for the most part, the water we drink that comes from the wastewater treatment plants is, for the most part, safe in a lot of municipalities, but in some it's not so great. Now, here's an example of how wastewater treatment works, and this may vary from plant to plant, but It just goes to show you there's a lot of processes that it goes through in order, for your water to be cleaned up and be suitable for consumption again. All right, physical properties of water. Water temperature is one of them. When we were studying hydroelectric dams, I explained that one of the problems with those is that they sometimes produce what we call heat pollution, and some factories do this as well, where they heat water above what is considered to be a healthy threshold for the water, and this can kill organisms that live in the water, while also favoring organisms that we need to keep in check, like bacteria and algae that can become too numerous and use up too much of the oxygen and deprive the other aquatic organisms of oxygen and cause them to die. Other physical properties of water are total dissolved solids and total suspended solids. Total dissolved solids are the combined living and non-living substances that are dissolved in water, meaning that you cannot readily see them. This water may seem absolutely clear to you, but it has living and non-living substances dissolved in it. And then we have total suspended solids. This is living and non-living substances suspended in the water that you can readily see. That's like if you scooped up water out of a river or stream, like the person in the picture is doing, and you look in there and you can see maybe a little bit of algae in there, and maybe some sticks from brush, or maybe grass clippings, or some soil that's in there, or maybe even bugs or other living things that you can actually see. That would be total suspended solids. So these are things that are looked at whenever you're trying to assess water quality. Like, what's the water temperature? Is it within the normal threshold for that environment? What's the total dissolved solids? Is there too much microscopic organisms in this water, making it unhealthy to drink, putting people and animals at risk for sicknesses? Then total suspended solids. How many things are floating around in the water that we can see? These, like I said, these are all things that are looked at when considering water quality. Furthermore, pH level is something that is tested for when assessing water quality. We want the pH level to be as close to 7 as possible, because 7 is neutral. It's not too basic, it's not too acidic at all. A little bit above 7, a little bit below 7, not really a big problem. But when you're getting, way below 7 or way above 7, that's when we have problems with the water quality. Dissolved oxygen is another property of water. There needs to be enough oxygen dissolved in the water. Low oxygen levels can kill the living things in the water. A lot of times, we think about aquatic species, and because they're underwater, we don't think that they breathe, but they actually do breathe. They breathe the oxygen that's dissolved in the water. They absorb it through their gills. So they do breathe. It's just a lot different than what we think about us and other animals that live above water. How we breathe, it is a lot different, but aquatic species still breathe. All right, the biotic index indicates the types and amounts of organisms present in an environment, and in this case we're talking about present in water. So we use the biotic index to measure water quality of a stream or river. And like I said earlier, we have lots of living things that are either dissolved or suspended in water in our environments. So, the biotic index measures from 1 to 10. Okay, so 0 on the scale is no apparent organic pollution, 0 to about 3.5. That's excellent water quality. That's water for which there's no indication that there's an overgrowth of organic material in the water. 3.5 to 4.5 is still considered to be very good. There might be slight organic pollution, but nothing that's going to harm you. 4.5 to 5.5 is still considered to be good. You have some organic pollution, but again, it should be okay. When we get above 5 and 5.5, we're starting to get into water that's not ideal. So 5.5 to 6.5 is considered fair, and they say there's fairly significant organic pollution. This is something you might, start getting concerned about. 6.5 to 7.5 is fairly poor, significant organic pollution. 7.5 to 8.5 is poor, very significant organic pollution. So now we're really like in the, we're kind of where this is water that, you may not want to use this water. You especially probably don't want to drink it. You might be risking sicknesses by doing it, some of which can be, very serious and perhaps even lethal. And at 8.5 to 10 on the biotic index, we're talking about water that is very poor. That's severe organic pollution. This may be water that just has too much bacteria in it, or eutrophication, which is like really overgrown algae in it, and that's just not suitable for use. All right, moving on now to watersheds and river basins. A watershed is an area of land for which all precipitation flows to a central location, which is pretty much always going to be the lowest lying spot on that landscape. So it doesn't always look like it, but areas of land can be kind of bowl-shaped, even if it's ever so slight. You don't need but the slightest little incline for gravity to take hold of water and allow it to run. I mean, I'm talking about just, a centimeter or two. As long as there's some kind of incline, water can run off and run across the surface of the land. Some areas of land are very, very bowl-shaped, such as in the mountains, where you have mountains and valleys that are very prominent. So watersheds, including river basins, are separated from each other by areas of higher elevation, like ridge lines and divides. And that's what I mean by having this kind of bowl shape. And you can see that in the picture. You have these areas kind of on the sides here. They're up higher in elevation than the area here in the middle. So just as all water inside of a particular watershed flows to one central location, the same is true for the pollutants carried by that water. Okay, so pollution in one area of a watershed can affect people, plants, and animals elsewhere in the watershed. So, I mean, any pollutant that ends up, like we've said already many times in this class, any pollution that ends up on the ground ends up in the water eventually. So you may not live right next to the river. You don't even be close to it, or whatever other central location there is in your watershed. But, if you allow pollutants to get on the ground, they're going to end up at that central location. And then because of that, end up elsewhere as well. So pollution, especially water pollution, it's never just contained to one area. There may be some areas that are worse off than others, but once pollutants get into the environment, it's not just going to affect that one location, especially not when water becomes involved, when precipitation falls on the land and starts to carry those contaminants elsewhere. All right, in North Carolina, there are 17 river basins, 4 of which empty into the Atlantic Ocean. Some flow down into South Carolina, and the remaining flow westward to the Mississippi River. Now, this is important to note, and if you notice about our rivers, too, in North Carolina, a lot of them come from up north. They flow into North Carolina from Virginia and Tennessee and elsewhere. So it's important for states to reduce the amount of pollution in rivers, not just for the sake of their own state, but also because it can pollute other states as well. And, it's not just enough to keep your state clean. It's important to make sure you're keeping other ones too. And that's the thing about our political boundaries between states and countries and so on and so forth. It's just artificial. There's not actually a boundary containing anything. The land is all still joined in together. So pollution in one state can affect another state very easily, or pollution in one country can affect another country very easily. So there is the potential for lawsuits and things like that. One state sues another because pollution flowing from one state via the rivers into the next. And like I said, the same thing can happen from country to country. You end up having lawsuits or other types of conflict because, one is polluting another because of the flow of water in rivers or by other means.